Next is long line modeling. So we are going to use a distributed parameters here. So we are going to represent something like this. This will be the sending end Vs voltage and the current Is. And somewhere along the middle of the line we will take a elementary length X. This is the impedance element, okay, and here we can take the admittance, right, and this again it will continue till we have the receiving end, and here the receiving end current is IR, voltage is VR. Now the voltage drop across this elementary element we will take as dV, right, there will be voltage drop all along the line. So across one elementary element we will take as dV, okay, and also the charging current. At each and every length there is going to be some charging current. Here there is going to be charging current, here there is going to be charging current all along the length of the line, okay. So at one elementary length what will be the charging current? We will take that as dI. Now if this current is I, then this current will be I plus dI by KCL, right. In a similar manner we can take the voltage here to be V, so that what will be the voltage at this part? It is going to be V plus the voltage drop across this, right. So it will be V plus dV. One important point that you need to know here is Vs is not equal to V plus dV, right, because this is somewhere at the middle of the transmission line. This is at the sending end and this is at the receiving end, okay, and also similarly Is is not equal to I plus dI. Similarly the receiving end side, VR is not equal to V and IR is not equal to I, okay. So this is just the basic, but you need to remember this point, okay. Next, X is the distance from the receiving end. And then finally Z is the impedance per unit length. This is small z. And what is the admittance? We will take as small y. So this is the admittance per unit length. Now this dV dI that is present here, the elementary current, this you can approximate as the voltage across this into the admittance, right. Now what will be the admittance? We have taken Y to be admittance per unit length. So for dx length of the transmission line, the admittance you can take as Y into dx, and the voltage what we will do, it is either V plus dV or V. We can approximate as V because dV is very small, so you can approximate the voltage as V. So using these assumptions, what will you get? dI is equal to the voltage which is V into the admittance which is Y dx, okay. So from here you can write dI by dx is equal to V into Y. So this is one equation. Similarly, you can write an expression for dV, okay. If you take this elementary length, for unit length the impedance is Z, so what will be the impedance for dx length? Z into dx, okay. So the voltage drop dV will be the current through it into Z dx. So the current once again you can assume as I. It is either I plus dI or I, right. So we can assume as I because dI is very small in comparison, okay. So dV is going to be I into Z dx, okay. So from here you can write dV by dx which is equal to I into Z. This is the second equation. Now we will differentiate equation 2. What will you get? d square V by dx square is equal to Z into di by dx, because Z is a constant with respect to the x. It is the impedance per unit length, right? So it is constant with respect to x. So only I is the variable. So we have Z di by dx. But di by dx we already know here, it is v into y, right? So this we can write as vy into z. Now this is a differential equation, right? So if you are going to solve this, then you are going to get v is equal to c1 e to the power root yz into x plus c2 e to the power minus root yz into x, right? This is the solution to differential equation. If we take it as 3, differential equation 3. Okay. Now here this y root over yz we can take as one variable called as the propagation constant gamma. Okay. So this is equal to root over y into z. Okay. So now v you can write as c1 e to the power gamma x plus c2 e to the power minus gamma x. Similarly, you can find I, right? Or you can, if in this equation dv by dx is equal to iz. So you differentiate the expression for v and divide by z, then you are going to get I. Okay. So you can write, I will write directly. Similarly, I you can get as root over y by z c1 e to the power gamma x minus c2 e to the power minus gamma x. Now just like the propagation constant here, we will assume another value which is the characteristic impedance ZC. So this we will take as the value root over z by y. Okay. So here root over y by z is nothing but 1 by zc. Okay. So current you can write as I is equal to 1 by zc c1 e to the power gamma x minus c2 e to the power minus gamma x. This is the expression for current. Now we still have these are arbitrary constants. We still have to find them. Okay. So you have to take some known condition here. What is that? At x is equal to 0, what will the condition be? This is the receiving end. And at receiving end, what is the voltage? VR. And the current is going to be IR. Okay. So these conditions, if you substitute in the expressions for voltage and current, then you can find the values of C1 and C2. Okay. So here I am writing the final values of V and I. V is equal to VR cos H gamma x plus ZC IR sin H gamma x, and the current I you will get VR by ZC sin H gamma x plus IR cos H gamma x. Okay. So this is the final value that you are going to get. At any value, if you substitute x is equal to somewhere between the line, you will get the voltage at that point. Okay. Similarly, current at that particular point we can get. Okay. Now whenever we are modeling, what is the final goal? We need to find the ABCD parameters, right? So we can find the ABCD parameters if you substitute here x is equal to L. At the sending end, the value of x is L, which is the length of the transmission line. Then you can get Vs and Is here. Okay. So here if you take L to be the length of the transmission line, then at x is equal to L, what will be the voltage? Vs. and current is going to be Is. Okay, so you're going to get Vs is equal to Vr cos h gamma L plus IR Zc sin h gamma L, and similarly the sending end current you're going to get Vr into sin h gamma L by Zc plus IR into cos h gamma L, right. So this here will be the parameter A, this is parameter B, C and D. So we can write in the matrix form, this is equal to cos h gamma L Zc sin h gamma L sin h gamma L divided by Zc, and finally cos h gamma L, Vr and IR. So here you can see that A is equal to D, right, because it is a symmetric network. So in the long lines we have the hyperbolic functions cos h gamma L and sin h gamma L. Okay, if we take this propagation constant to be having a real and imaginary part, it will have a real and imaginary part. So if we take that to be alpha plus j beta, then alpha is called as the attenuation constant and beta is called as the phase constant. So this unit is radians per unit length. Okay, and attenuation constant we take as Nepers per unit length. Now what will happen if you take the case of cos gamma L? So this is going to be what? E to the power gamma L plus e to the power minus gamma L divided by 2. Now instead of gamma you substitute alpha plus j beta L plus e to the power alpha minus alpha plus j beta L divided by 2. This you can write as e to the power alpha L into e to the power j beta L plus e to the power minus alpha L e to the power minus j beta L divided by 2. Now this is a phasor. E to the power j of something will be a phasor of what? Unit magnitude. And what will be the phase? Phase will be this function here, this variable here. Okay. So here you can write this as e to the power alpha L angle beta L. Similarly, e to the power minus alpha L angle minus beta L divided by 2. This is the cos h gamma L. Similarly, you can write for sin h gamma L. This will be 1 by 2 e to the power alpha L angle beta L minus e to the power minus alpha L angle minus beta L. So these expressions, they will help you to calculate the hyperbolic functions easily. Now in order to analyze the long line, we have found out the ABCD parameters. So now what we can do is, we can make use of an equivalent network which is in the form of a pi network using lumped parameters. Okay, but the parameters that are associated with that network is ABCD parameters of the long line that we have derived. Okay, so for example, if you take, this is the impedance, series impedance, and here you have the capacitance. So these are not the actual impedance and admittance of the lines. We will take this as Z dash to differentiate from the actual impedance, and this we will take as Y dash by 2, Y dash by 2. Okay, here Z dash and Y dash are not actual impedance and admittance of the line. Okay, and also here you can write this is a lumped parameter network whose ABCD parameters are equal to that of the long line. Now what we will do is, this network we will find the ABCD parameters and we will equate it to the ABCD parameters of the long line. In that way we will get the expressions for Z dash and Y dash in terms of the parameters of the long line. This we can get from the nominal pi network analysis that we've done for medium lines. Okay, from nominal pi network analysis of medium lines, we know A is equal to D is equal to Z dash Y dash divided by 2 plus 1, and B is equal to Z dash, and C is equal to Y dash into Z dash Y dash by 4 plus 1. And we have the ABCD parameters of long line. A is equal to D is equal to cos H gamma L. B is equal to ZC sin H gamma L, and C is equal to 1 by ZC sin H gamma L. So from these two we can get the relation between Z dash Y dash and the parameters ZC and gamma and L of the long line. Okay, so we are writing the final expression here, equating these relations. We finally get Z dash is equal to Z sin H gamma L divided by gamma L. Here Z is the impedance of the entire line, okay, where Z is impedance of entire line. Okay, or you can write it in terms of the characteristic impedance as ZC sin H gamma L. Okay, and next is Y dash. This is going to be Y into tan H gamma L by 2 divided by gamma L by 2. Okay, where Y is the admittance of entire line. Okay, or you can also write in terms of the characteristic impedance as 2 tan H gamma L by 2 divided by ZC.